This video is about the Oxo Acids of Phosphorus. Hypophosphorus acid has the formula H3PO2. On checking the oxidation state of phosphorus, one is able to understand that it is carrying +1 oxidation state. The molecule assumes a tetrahedral structure wherein P is the center point and around P we have a double bond which is forming the apex of the tetrahedron. The rest of the atoms are arranged at the corners of the tetrahedron as bond OH. The remaining hydrogens will be arranged at an angle of 109 degree 28 minutes. So this becomes the structure of phosphonic acid, otherwise known as hypophosphorus acid. On checking the formula, one is able to understand that there are two pH bonds here. The number of pH bonds will help you understand whether it is acting as a reducing agent or not. Here, since two pH bonds are there, it can very well act as a reducing agent. Coming to the oxo acid, here we find that one hydrogen is in turn attached to the oxygen. This is the acidic hydrogen or the replaceable hydrogen. So the basicity or the strength of the acid is decided by the replaceable hydrogens. So here we find that only one replaceable hydrogen is there, and so basicity is 1, and we can call it as a monobasic acid. So what all properties have we seen for phosphonic acid? It is a monobasic acid. It is also used as a reducing agent. Coming to the next molecule, Orthophosphorus acid, otherwise known as phosphonic acid, has the formula H3PO3. On calculating the oxidation state, we have -2 on oxygen and +1 on hydrogen. So the total effect is it is having +3 oxidation state on phosphorus. Now coming to the structure of orthophosphorus acid. Here P will form the center. We have P double bond O at the apex, and the rest of the atoms are arranged at the corners of the tetrahedron. So bond OH, one more bond OH, and the rest it is hydrogen. So on examining the structure, we can understand that one pH bond is there, so it can act as a reducing agent. How many replaceable hydrogens are there in the molecule? We find two replaceable or acidic hydrogens are there, so it becomes a dibasic acid. The next oxo acid is Pyrophosphorus acid that comes in the set. It is got by heating two molecules of orthophosphorus acid. This molecule contains two replaceable hydrogens, so it is a dibasic acid. It also possesses two pH bonds, so it can act as a reducing agent. So the formula of the compound becomes H4P2O5 with +3 oxidation state. Phosphorus is found to have +3 oxidation state. Now check the nature of the molecule. Here you find two replaceable hydrogens are there, so it will be dibasic in nature, and here you find that two pH bonds are there, due to which it can also act as a reducing agent. From the structure, one is able to understand that pyrophosphorus acid is a dibasic acid. Next is
and
orthophosphoric acid
as
with
a
the
reducing
formula
agent.
H3PO4. You find that the oxidation state becomes +5. And so the structure is again a tetrahedral structure with P double bond O at the apex, and we are going to arrange OH at different angles. So you get H3PO4. Now tell me whether you are able to identify it as a reducing agent. Here we don't have pH bonds. It is not a reducing agent. Instead, it can supply oxygen to others, so it can act as an oxidizing agent. How many replaceable hydrogens are there? You find it is 3, and so this is a tribasic acid. We shall now draw the structure of pyrophosphoric acid. So when it is pyro compounds, you find that it is formed by heating the orthophosphoric acid. We require 2 molecules of orthophosphoric acid side by side. When a molecule of water is removed from 2 molecules of orthophosphoric acid, we get the structure of pyrophosphoric acid. So what will be the structure of the molecule? You find it is 2 tetrahedrons joined at one corner. Here too, we find that there are 4 replaceable hydrogens. So this is an example for a tetrabasic acid. This doesn't have pH bonds in it, and so this cannot act as a reducing agent. The molecule is not a reducing agent. It is an example for a tetrabasic acid with the formula H4P2O7. The next molecule is hydrophosphoric acid. Here the tetrahedra are joined only through pp bonds. So the structure becomes a planar molecule with 4 replaceable hydrogens, that is 4 acidic hydrogens are present, and so it is a tetrabasic acid. It cannot act as a reducing agent as there are no pH bonds in it. What will be the oxidation state of phosphorus in the molecule? Here you find that oxygen is carrying -2, hydrogen is carrying +1. So with the result you have +4 as the oxidation state for phosphorus. For drawing the structure of Cyclo Metaphosphoric acid, we require 3 orthophosphoric acid side by side. So I am drawing P double bond O, single bond OH, OH here, 1 OH this side. Again, I'll draw P double bond O, single bond OH, this side 1 OH and another side 1 more OH. Again, P double bond O, single bond OH, 1 OH here and the other OH this side. We are going to remove 3 molecules of water from this. Just see how it is removed. 1 molecule of water, second molecule of water, third molecule of water. So this is the ring structure of cyclometaphosphoric acid. On examining this formula, you find that it is H3P3O9, which can be written as HPO3 thrice. The molecule is tribasic. This is not a reducing agent. From this, we can prepare the polymetaphosphoric acid. On heating the compound, the ring breaks and we get a linear chain of polymetaphosphoric acid. Suppose that the molecule is broken from here, we'll have a linear chain in which the P double bond O will be arranged alternately. The repeating unit of the molecule has the formula HPO3 n times.